When we have a set of model results based on our estimated model inputs, we often want to measure the impact of overall uncertainty on results. We can do this using Probabilistic Sensitivity Analysis. We call it PSA. PSA runs a series of model recalculations, each one using a different set of samples for parameter distributions. Some recalculations will confirm our base case, others will not. The more recalculations that confirm our base case, the more confidence we have in our results. We'll use this cost-effectiveness analysis Markov model to demonstrate PSA. After generating the cost-effectiveness analysis graph, we can see the ISA via clicking through the text report. On this model, we see the base case ISA is 26,299, indicating treatment 2 is the preferred strategy, relative to a willingness to pay of 50,000 per quali. Within the model, we will focus on uncertainty from 4 parameters. In order to perform PSA on those parameters, we need distributions for each of the 4 parameters. We can then sample from those distributions as opposed to using the base case point estimates. 3 of the distributions are already defined in the model. In the distributions view, we'll create the 4th distribution. Use the green plus to add a new distribution. We'll select the distribution type first, which is going to be a beta distribution. And then we'll give it an appropriate name. This one will be called dist p local to METS 2. For this distribution type, you can have alternative parameters to parameterize it. So a beta distribution can use alpha and beta parameters, or your mean and standard deviation. With the alternative parameters selected, we'll enter a mean value of 0.13 and a standard deviation of 0.01. Importantly, we need to select to resample per expected value, which will ensure that this distribution is resampled for each model recalculation within PSA. The PDF and the CDF graphs will show you the shape of the underlying distribution. Once you're happy with the distribution shape, select OK. There's other useful information you can find when creating the distributions. When we run base case results on the model, the distribution mean will be used rather than samples. You can use this override the mean button here if you need to change that mean value when you're running base case analysis. Use the help icon down here at the bottom left to enable you to access documentation, including the formulas Triage Pro uses for each parametric distribution. Once the distributions are created, the model needs to reference them. We have the variable p local to METS 2, which is currently equal to a numeric value. We edit this root definition, and we're going to set it equal to the distribution. We don't replace the variable with the distribution. Replacing the variable with the distribution would mean we can no longer do deterministic sensitivity analysis. And also keeping the variable will still allow us to do this. So let's consider how this parameter will be used in base case analysis and sensitivity analysis. In base case analysis, the variable references the distribution mean, or the override mean button, for a single calculation. When you do univariate sensitivity analysis or tornadoes, it will apply to a range of values for the variable parameter. And when you do PSA, it will use a set of samples from this distribution. To run PSA, select the root decision node, and then choose Analysis, Monte Carlo Simulation, and Sampling from the menu. The original model is a cohort model, but if we were doing microsimulation, we'd also select Sampling and Trials. Next, we select the number of samples, which is 1,000, and then run Analysis. The primary output shows the aggregated results over all 1,000 samples. These are usually similar to base case results. However, it's the PSA outputs that provide the useful information about the impact of uncertainty. There are many PSA outputs. We'll focus on the ones which are most commonly referenced and reviewed. The All Data report shows the raw data from each model calculation. On the right-hand side, we'll see all the distribution samples used for that calculation. On the left-hand side, we see the analysis output from each strategy using those distribution samples. Notice the optimal strategy is highlighted for each model calculation. Optimal strategy is determined as the one with the highest net monetary benefit using the willingness to pay from tree preferences. In the original model, we can generate the CE analysis graph with a single set of parameters. This is a single result of an expected value calculation. In PSA, we generate the CE scatter plot to see the variance in output generated from the different sets of sample parameters. This graph illustrates the overall impact of uncertainty, but other outputs better illustrate confidence in our base case results. The ICE scatter graph is run for any pair of strategies. In this model, we have only two, but compare the most costly to least costly. This will give positive incremental outcomes. Each point represents a single iteration as an incremental cost versus an incremental effectiveness. A point in the top right quadrant indicates that treatment 2 was both more costly and more effective than treatment 1. The willingness to pay line splits up that quadrant between the points with an ISA less than a willingness to pay and points with an ISA greater than willingness to pay. In fact, the willingness to pay line splits all model calculations between below and right of the willingness to pay line that favour treatment 2 in green and those above and left the willingness to pay line that favour treatment 1 in red. The ellipse contains 95% of the model calculations. Note the setting options to the right to change the graph's appearance. Lastly, we have the acceptability at a willingness to pay, which shows the number of iterations which support each strategy for the default willingness to pay as set in the tree preferences. We can see this split among strategies over a range of willingness to pay using the acceptability curve. Specifically, you see the percentage of model calculations that favour each strategy. These and additional outputs will provide you an understanding of the confidence in your results when running PSA.